let's see what's going on at that slit. So they put detectors here. These little red things are just symbols for detectors. And they said, let's see what's going on with those at those slits. So they put a detector there, and this detector was not going to be able to interfere with the light. It was non-interactive with the light. So they ran their detector, and sometimes they would get a detection of a photon here, and when they did, they'd get a spot of light there. And sometimes they'd get a detection of a photon here. Whenever they did, they got a light there. Now suddenly, they got the answer they were looking for when they detected. And then they turned the detectors off, and they got this pattern again. Okay, big problem. So the next thing they did was to say, well, it must be those detectors, right? Those detectors are somehow doing something. Well, that was almost right. It wasn't really the detectors, because either by luck or by brilliance, somebody decided to leave the detectors turned on, detecting, but not collect the data. In other words, let's say the detectors were sending little electrical pulses. Every time a photon went through, a little pulse would go up, and that would be recorded. It would go to a tape head, and that would be recorded on a magnetic tape as a little blip, and then they'd count the blips. Okay, well, this then, leaving the detectors on but not taking the data would be like you just don't mount the tape. So the tape head's still having little pulses going on it, but there's no tape in there, so they're not being recorded. Okay, well, what do you think happened when they did that? When they had the detectors operating but didn't collect the data, they got this. So it wasn't the detectors that were causing the difference in the pattern. It was whether or not they collected the data. Well, collecting the data is a human function, you see. That's a consciousness. That's an individual person. Data doesn't collect itself. That requires a consciousness. That's why quantum mechanics then drove this philosophical problem of consciousness is at the root of reality, because consciousness seems to make the difference of whether we get particles or not. Well, our whole world is made up of these particles. Now you think, well, photons are kind of funny particles, right? They have no mass, they go to the speed of light. That's not like real things. But then they did the same experiment with electrons, which are massive little particles, even with hydrogen atoms, anything that was small that they could get a diffraction pattern with, found it worked exactly the same way. You don't take the data, you don't get the particle. Okay? Let's do the next one. Here was the answer to this. The answer to it was produced by Erwin Schrödinger. He was a German graduate student at the time. You probably noticed that in physics, all the big breakthroughs are done by young people. Most of them are done by people in their mid-20s. Very few are done by anybody over, out of their 20s. Einstein started writing his theory of relativity when he was in his 20s. That's typical. Why? Because they haven't been around long enough to understand what's impossible. That's why. So anyway, Erwin Schrödinger, he looked at this and he said, well, this sort of looks like a probability distribution. You have a photon that comes in here and it has some probability of going here or here or here. Obviously, it's breaking up and there's some probability. It looks like a probability distribution because it's big at the center and then tapers off, gets smaller and smaller. The light spots get less and less dense as you go out, and it's symmetrical on both sides. So this is sort of like it goes this way and then there's a peak and then it comes down like that. So he said, well, let's just describe it in terms of probability. And he did that. He said, we'll just assume that there is no photon. It's just a probability distribution. And that some of that probability distribution will go through this slit and some of it will go through that slit. And guess what? Let's let that probability distribution interfere with itself like a wave would by some integral number of half wavelengths. Okay, which doesn't mean much to a probability distribution, right? He just made this up because he thought it would get the right answer, and it did. He was able to get the right answer. He could get this distribution, which is what happened. Well, the physicists of his day, of course, didn't pay much attention, and that's just a graduate student, finagling the answer, right? Using math to come up with the right answer, because it didn't mean anything. It didn't have any physical interpretation or significance. So it was discounted at first. But then because there was no other theory, it was applied to other situations. And sure enough, it worked there too. Then it got developed more and more, and that turned into quantum mechanics. That was the beginning of the science of quantum mechanics. It's called wave mechanics now. And these are probability waves. Okay, they're probability distributions, and they're waves because they combine like waves. So they're called probability waves. All right, here was the answer, and that is that Because this is a probability distribution, now again, we're saying particles are not particles. There is no massy particles. They're just probability distributions until somebody makes a measurement. And as soon as you make a measurement, that probability wave collapses. Scientists say the probability wave collapses to form a particle in the physical reality. Okay, this was science, basically goes back now about 50 years, 60 years. Okay, so the measurement creates the particle. Before the measurement, the particle is non-physical. It's just probability. Okay, all right. Spend a little time on that because that's real kind of critical to understanding the nature of the physical world. Okay, here's some quotes from some of the guys who actually developed quantum mechanics, some of the original people who figured all this out. Eugene Wigner. It will remain remarkable in whatever way our future concepts may develop that the very study of the external world led to the scientific conclusion that the content of the consciousness is the ultimate universal reality. Okay, now this is a Nobel Prize winning physicist. Then Max Planck, who's often known as the father of quantum mechanics. He didn't invent it. The graduate student did, but you know, we don't give graduate student credit. Besides, Max Planck developed a great deal of what is now quantum mechanical theory. He was the genius behind putting a lot of it together. And he said, science cannot solve the ultimate mystery of nature because in the last analysis, we ourselves are part of the mystery we're trying to solve. Okay, that's like Einstein saying that space of physics is a function of our conceptual scheme. In other words, what's out there, physical reality, is entangled with what's in here, consciousness. That was the result. Okay, so a probability is not a physical particle. Okay, then if it's not a physical particle, let's just call that a non-physical particle. That's a not physical particle, right? It's a representation of a potential particle, a probable particle, that's all. Non-physical must precede the physical. It's a probability distribution before it can be a physical particle. Cause must precede effect. Okay, you take those little two pieces of logic together and you say the physical is the effect. This reality, this universe is the effect. The non-physical is the cause of the effect. Okay, so that's where science takes you. All right, now let's jump up a few decades up to from the early 1900s up to the late 1900s. In 1992, we have Edward Fredkin, another distinguished physicist, world-class physicist known all over. He started a movement within the physics community called digital physics, and that's a live and growing movement today. He came to the conclusion that reality is either a computer itself, implemented on a computer like a simulation. It's essentially digital. It's essentially informational. Okay, now he came at this, he's a physicist, but he came at this not only through physics but through information theory. He presented this at a physics forum presentation. It cannot be, the reality cannot compute itself, so it has to be computed somewhere. And of course the first question to Fredkin is, Dr. Fredkin, okay, if it's a simulation, who's simulating it? Where's the simulation being done? And Fredkin said, in other. He says, I don't know. Equations don't take me there. Science only tells me that it is so. Says that the science in experiment says that time is digital, discrete chunks, it's not continuous. Space is digital, discrete chunks that aren't continuous. Now those two weren't new ideas. Max Planck had already computed the Planck length, which is about 10 to the minus 35 meters, which is where he said that space becomes granular. In other words, you get down to the pixel level. All right? And he also computed the Planck time, which was where time also becomes granular. So those ideas had already been around in quantum mechanics, but Fredkin kind of reproved them from an independent methodology. Okay, next on the list was Nick Bostrom. Nick Bostrom is a chairman of a department at Oxford, no lightweight physicist. He has degrees both in physics and in philosophy. He wrote a paper called You're Living in a Computer Simulation. And he started out with taking this as a philosophy and physics problem. He says, can we prove that that's impossible.